What are algorithms in AI? In the fascinating realm of artificial intelligence, AI, algorithms stand as pivotal components that breathe life into machines, enabling them to execute tasks and make informed decisions. Think of an algorithm as a precise set of rules or instructions meticulously designed to tackle specific problems and achieve particular goals. Within the vast expanse of AI, algorithms are indispensable, facilitating machines in learning from data, uncovering patterns, making predictions, and autonomously executing tasks. Algorithms are indeed the backbone of AI systems, empowering machines to process massive volumes of data, extract insights, and take actions based on these insights. These intelligent procedures span a wide range of types, tailored to the unique problems they're designed to solve and the kinds of data they handle. Such algorithms delve into all potential solutions to a problem, sifting through them to identify the most optimal one. Imagine navigating a maze. These algorithms guide the process of finding the shortest path in navigation systems or even strategizing in games like chess. By evaluating various possibilities, they determine the best course of action according to predefined criteria. A common such algorithm finds the shortest path by assessing both the cost to reach the current point and the projected cost to reach the goal, a process foundational in pathfinding and graph traversal. Classification algorithms excel at sorting data into predefined groups or categories. They find application in diverse tasks such as spam detection, image recognition, and medical diagnosis. By learning from labeled data, where each data point is associated with a category, these algorithms eventually classify new, unseen data effectively. What are algorithms in AI? Example, the support vector machine, SVM, is a classification algorithm that identifies the optimal boundary dividing data points into distinct categories. Regression algorithms shine when predicting continuous values based on input data. They are invaluable in scenarios like forecasting house prices, sales trends, and temporal analysis. By understanding the relationship between input variables and a continuous output variable, these models facilitate accurate predictions. What are algorithms in AI? Example, a linear regression, a straightforward regression approach, fits a straight line through data points to model the relationship between two variables. In the absence of labels, clustering algorithms autonomously group similar data points into clusters based on shared characteristics. This unsupervised learning approach aims to uncover hidden patterns or structures in the data, and is often utilized in market segmentation, image analysis, and understanding customer behavior. What are algorithms in AI? Example, K-means clustering effectively sorts data into K-groups, assigning each data point to the cluster with the nearest mean. Optimization algorithms target the minimization or maximization of specific objective functions. They are essential in finding the best solution from numerous possibilities, particularly in machine learning for fine-tuning model parameters during training. Example, gradient descent, an optimization algorithm, is paramount in training machine learning models by iteratively adjusting parameters to minimize prediction errors. Reinforcement learning algorithms allow AI systems to learn interactively with their environment, receiving feedback through rewards or penalties. Through trial and error, these systems aim to maximize cumulative rewards applicable in autonomous driving, gaming, and robotics. What are algorithms in AI? Example, Q-learning enables an agent to optimize actions in an environment, seeking to maximize expected cumulative rewards. AI algorithms thrive on data. In supervised learning, algorithms train on labeled data, connecting data points to corresponding outputs. In unsupervised settings, they discern patterns without labels. Increased data exposure enhances predictive accuracy. During training, algorithms construct models mapping inputs to desired outputs. In classification, models define boundaries segregating categories, while in regression, they capture relationships between variables and outcomes. Post-training, algorithms undergo testing with fresh data to gauge performance. Metrics like accuracy, precision, and recall measure task execution. For instance, a classification algorithm's accuracy reflects the proportion of correctly classified data points. Optimal performance demands algorithm tuning. Adjusting hyperparameters like learning rates or neural network layers ensures generalization to new data, preventing overfitting to training data. Decision trees, simple yet potent, are used in classification and regression. They methodically split data based on feature values, visually resembling a tree as each node represents an attribute-based decision. Random forest, an ensemble learning method, amalgamates numerous decision trees for heightened prediction accuracy. It mitigates overfitting risks by training each tree on random data subsets. Neural networks, particularly in deep learning, tackle complex tasks like image recognition and natural language processing. Composed of node layers, they process data to uncover intricate patterns. KNN, a straightforward yet effective algorithm, leverages proximity to predict data point labels by assessing k-nearest neighbors classifications. Naive Bayes, a probabilistic algorithm, applies Bayes' theorem in classification tasks. Its simplicity belies its effectiveness in scenarios like spam detection. Overfitting, when an algorithm excessively specializes in training data, hinders new data performance. Techniques like cross-validation and regularization help models generalize effectively. AI algorithms may inherit biases from training data, potentially reflecting societal inequities. Ensuring fairness demands nuanced data collection and algorithm design. The crux of algorithm success lies in data quality. Issues like noise or inaccuracies undermine performance, necessitating rigorous data preprocessing, from cleaning to feature extraction, to optimize training preparation.